Hello, my name is Paula, and this presentation is a complement to the poster on the Pore-scale analysis of gas injection in gas condensate reservoirs, which I conducted with Professor Márcio Carvalho. So, starting with a brief introduction, this study was motivated by the challenges in production from gas condensate reservoirs, which undergo transition from single-phase to two-phase flow during depletion. And I'll explain that using this phase diagram of the reservoir mixture and this reservoir wellbore scheme. So if this arrow here represents the reservoir isothermal depletion, at high pressures we are in the single phase region, where there's only gas flowing from the reservoir to the wellbore. However, at lower pressures we enter the two-phase region, where condensate dropout takes place. And in this case, far from the wellbore we still may have the single phase gas flow, but close to the wellbore we shift to a two-phase gas condensate flow. And this is a problem because this condensate blocks many of the gas flowing paths and reduces a lot the well productivity in a phenomenon known as condensate blockage. So a possible remediation for this problem is to inject gas in the reservoir, and with that we can achieve partial or full pressure maintenance and also revaporize that condensate that had accumulated before. This method has been investigated through core flooding experiments and compositional reservoir scale modeling, but no Pore-scale evaluation has been reported in the literature. So in this context, our goal was to evaluate condensate revaporization in porous media with gas injection at the Pore-scale using a pore network model. So now I'll explain this study's methodology, and basically what we did was to reproduce gas flooding following condensate banking using a compositional pore network model for gas condensate flow. The main features of this model are the fact that we represent the porous medium as networks of converging, divergent, circular pore elements, that in those pore elements we've implemented transport rules specifically devised to represent condensate dropout and the coupled flow of gas and condensate in the porous medium, and that the compositional formulation we used was based on the work of Collins and others in 1992. And in these formulations, the phases are separated using flash calculations at constant pressure and temperature using the Pengen-Robinson equation of state. So using that model, here is the gas injection procedure we followed. So given a network representing the porous medium, which in this study was a sandstone-based network with an absolute permeability of 169 millidensity, a porosity of 17.1%, and a total volume of 1.75 cubic millimeters. So in this network, we implemented two different steps of injection. The first to promote condensate accumulation in this network, and the second to try to produce this condensate with gas injection. So in the first step, we've injected 25 pore volumes of this mixture here that represents the reservoir fluid. This step was carried out at the temperature of 60 degrees Celsius and at those 6 different pressures to represent different levels of depletion in the reservoir. And with that, we accumulated condensate in the network. Then we've implemented the second step, in which those gases here were injected. Those gases were either carbon dioxide, nitrogen, methane, ethane, or produced gas. We also injected 25 pore volumes and evaluated how much of the condensate we could produce. And the reason why we chose those gases besides the produced gas to try to revaporize condensate is because they could display a significant reduction in the liquid saturation when mixed with the reservoir fluid. And we can see that in those graphs here. They represent the liquid dropout as a function of pressure in the continuous line for the reservoir fluid, and in the dashed lines we have mixtures of that reservoir fluid and those gases. Here on top in those mixtures we have 50% in moles of those gases, and here at the bottom we have mixtures with 75% in moles of those gases. And we can see that in both cases we could achieve a significant reduction in this liquid dropout. So that indicates that those gases are good candidates to revaporize the condensate. And now moving to the results. In this presentation, I'll focus on the effect of pressure on condensate recovery during gas injection. So in this first slide, we'll see some graphs representing the condensate saturation evolution during the two steps of injection. So here we have the condensate saturation as a function of the injected pore volumes. So we can see that in the first 25 injected pore volumes, we have a condensate build up in the networks. And then in the last 25 injected pore volumes, we have a reduction of this condensate saturation due to the gas injection. And each of those colors represent a different injected gas. So we could realize that at high pressures, we had a fast liquid recovery, and also we could see that all tested gases could reduce significantly the condensate accumulation. We can see here that the CO2 and C2 recover almost all of the condensate that had accumulated before, and that the other three gases, they leave more or less 8-7%, so they all perform well. And then as the pressure was lowered, we start seeing that this recovery process became much slower, and also we could see a great contrast between the results of the different injected gases. So while for this pressure here, the injection of C2 and CO2 still could reduce a lot of the condensate, the other three gases didn't perform so well. And finally, at the lowest tested pressure, we could see that the recovery process became very inefficient, and all tested gases performed similarly. We can see here that there's no big difference between the lines, and they all leave most of the condensate behind. And to illustrate these results better, here we have illustrations of the CO2 content in the networks after the CO2 injection. And each of those networks represent different injection pressure. In yellow, we have high contents of CO2, and that indicates that in that region the CO2 could remove the condensate, and in purple we have low content of CO2, meaning that that region was bypassed by the CO2 injection. And we could see that from 22 megapascal down to 19.5, we had a progressive reduction in this volume swept by the CO2, but still the recovery of condensate was very high. Then at 17.75 megapascal, we started seeing a significant reduction in the volumetric sweep efficiency during the CO2 injection. And finally, we can see the lowest tested pressure, in which most of the volume was bypassed by the CO2 injection. And finally, here, just to compare the CO2 with the other gases, we can see on top the same results, but now for the injection of methane, in the middle for the injection of ethane, and at the bottom for the injection of nitrogen. And again, we can see that at high pressures, all of those three gases, they performed well to recover the condensate. At intermediate pressures, we start seeing those big differences between the gases. While the ethane could recover most of the condensate, the methane and nitrogen, they bypassed already most of the network volume during the injection. And finally, we can see that at 14.75 megapascal, none of the gases recovered the condensate well. So as the conclusions of this part of the study, we have that a procedure to evaluate condensate recovery with gas injection at the Pore-scale was successfully implemented, that this method can be effective to eliminate condensate banking depending on the injection parameters, that the injection of ethane and carbon dioxide display the overall most favorable results, and that this Euro method was significantly more effective at high pressures. And as future work, I think that it would be interesting to evaluate both the effects of gas injection rate and porous-mediated heterogeneity in the recovery of condensate. And to conclude the presentation, I would like to thank all the agencies that funded this work and everyone for watching.